Hi, ladies and gents. We've been talking about bonding, and we have been talking about all the different kinds of bonding. When nonmetals bond with metals, those typically are going to be ionic bonds. And when nonmetals bond with other nonmetals, those are typically covalent bonds. But what happens when metals interact with other metals? Well, that's a very special kind of situation referred to as the metallic bond. Now, what we're going to talk about is going to be a very, very quick overview. This is a huge topic, and that's why people get whole PhDs in metallurgy, in understanding how metals interact with other metals. So I just want to give you a quick introduction to this whole process. One of the things that metals can do is alloy. Now, alloy means that the metals are mixed. So this is more like a mixture than any sort of a bonding process. When everything is molten, they are stirred together in a pot and then allowed to cool. And what happens is the properties of both materials are then mixed together. And I think one of the funnest ones to talk about is gold, because many of us have a gold wedding band or piece of jewelry that's important to us, or we have inherited one from someone older than us. Now, 14 carat is an old unit that has been used for many, many years to express the purity of gold. 24 karat gold is pure gold. No other atoms are mixed in. If you buy most kind of high-end gold jewelry, it's going to be 18 karat. That means it's 18 parts gold and 6 parts other things, because the total has to add up to 24 parts. Now, the other parts are going to be usually zinc, nickel, copper, some combination of those things. Why do they mix other metals in with gold at all? Well, gold is very, very soft. It is so soft that if you're going to try and make beautiful jewelry out of it, the problem is that if it gets banged on a countertop or squished in any way, it will lose its shape. And if a jeweler's going to spend a lot of time making this beautiful piece of jewelry, they would like to have that beautiful piece of jewelry hold that shape more than once or twice that a person wears it. If you buy a little bit less expensive gold jewelry, and this is truthfully what most of us are going to buy, we're going to get 14 karat gold jewelry. That's 14 parts gold and 10 parts other metals. It's still going to have the non-corrosive properties of gold, but it's going to be a little bit stronger. It's going to, as we mix in these other metals, it's going to become a little bit harder, a little bit more brittle, and a little bit less soft. That's going to happen as we change this. As gold jewelry gets mixed down more, you can actually buy 10 karat gold. And as far as I know, that is the lowest quantity of gold that is legal to be still called gold jewelry. That gold jewelry is going to be a little bit more brittle, and so you have to be a little bit more careful with it. I've included these pictures because I also want you to notice that gold jewelry's color will change from 10 karat up through 14 and 18 karat. It will tend to get a little bit more golder as you get a higher percentage of gold. So what's going on with metals, and how does this metallic bond actually explain what's going on with metals? Well, metals have a couple really unique properties. One, they're malleable and ductile. That means they can be pounded into shape and stretched into wire. You cannot do that with covalent and ionically bonded substances. Metals are also really good electrical and heat conductors. So there's something going on at an atomic level that allows all of these things to occur. Well, to understand that, you've got to understand the atoms in metals. On the periodic table, all of these lovely metals over here have 1, 2, or 3 outer electrons are the most typical. They hold these valence electrons weakly. Metals tend to be the atoms that donate or give their electrons. Because they do not hold on tight to their valence electrons, these outer electrons out here are very, very loosely held. if you have a piece of metal, what happens between the individual metallic atoms is there is a sea of free floating electrons. So which atom does that electron belong to? Does it belong to that atom or that atom or that atom? Nobody really knows. The atoms don't know and the electrons don't know. There is really a kind of a fuzzy-wuzzy cloud of electrons in between the metal atoms. And it's this fuzzy-wuzzy, free-floating cloud of electrons that holds the metals together and creates the really interesting properties of metals. Now, metals, as I mentioned, are malleable and ductile. If you take a piece of metal and you beat it with a hammer and you want to change its shape, what happens is the electrons just kind of smear out of the way. If you try and do this with a brittle covalent or ionic compound, it's going to crack and it's going to break. But metals just kind of go, ooh, and they just sort of smear. The electron cloud is soft and fuzzy-wuzzy enough that it holds the whole thing together even when you change its shape dramatically. I found this picture online. I thought it was quite fabulous. This big statue that was made all out of aluminum foil. I thought, that's cool. If I had that talent, I'd do that too, but don't have that talent. Now, this ability to be pounded into shape, again, is due to this fuzzy electron cloud. Being able to pull it into a wire as being ductile, same sort of thing. You try and pull these atoms into a long, skinny piece. The electron cloud will hold all the atoms together, and they just kind of go with it. They flow around the atoms and hold them together. Where a covalent and ionically bonded substance, they're going to cleave or break. Metals are good conductors of electricity, and electricity is basically the movement of electrons through material. So if here is a picture of the atoms in my metal, let's say I want an electrical current to go through that substance. Here's how this works. This electron is going to bang into that electron, which bangs into that one, 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 and the electricity is going to come out the other end. It is because of the fact that these electrons are free to move that makes these metals really good electrical conductors. If you had something that was covalently bonded or ionically bonded, like this crystal of salt, the electrons are going to be locked in place. They are locked in the vault. This little atom right here is locked in place. It is not going to move. You try and pass electricity through there and the electricity is going to hit and it's going nowhere, because there is no way for the electricity to get to the next thing unless it has a huge, massive jump like a spark, and that's going to require tens of thousands of volts of electricity. This, boom, 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 the electricity is going to flow very, very easily. Small amount of current, small amount of amperage, and the electricity is just going to go. Again, due to this fuzzy-wuzzy cloud of electrons hanging around the metallic bond. Metals are also really good heat conductors. Now, heat happens to be the motion and vibration of atoms. If something is hot, atoms vibrate fast. If something is cold, the atoms just vibrate more slowly. So if you've got an atom out here that's hot, it bangs into this atom. And because these guys are all kind of free floating, this atom can bang into that one, which bangs into that one. Because nobody's locked in place, the heat can travel quickly from one place to another. If I've got a pot on the stove, the atoms in the bottom get hit very quickly, and the heat can get conducted from the bottom of the pot into the top of the metal layer and then into the food or the water, whatever you're cooking, very quickly, because of the nature of this wild and crazy, very unique way that metals are structured. So we will come back next time and talk a little bit about hydrogen bonding, and that will do for the moment. See you later. Bye-bye.